Okay, everyone tuning in virtually and in this room, it's 10:40, so we will begin our next talk, which is Lee Thornhill.
Hi, everyone. Can you hear me? Yep, you can hear this. I'm not going to talk about any particles in this talk, so something a little different. We're going to be looking at the winds and state parameter measurements that we made on the Falcon. Like I say, I'm Lee Thornhill. The real brains of this operation is John Barrick back at Langley, who nothing could be done without him. And there's my contact info if you have any questions. There we go. All right, so just in general, how do you compute the winds? It's basically geometry. It's a vector difference between the velocity of the aircraft with respect to the Earth and the velocity of the air with respect to the aircraft. You take the difference in two really big numbers and you get one very small number. And then you have a bunch of considerations like what is the temperature, as we've talked about a couple of times. People are interested in making sure the temperature is right, the pressures, you have differential pressure measurements, all this gets combined, and then you get an idea of your horizontal and vertical winds. There's a bunch of little corrections we'll get into and how this goes, but down at the bottom right, if you're flying straight and level, is essentially the platform velocity of the aircraft, which is the terms with the subscript P minus the speed of the air with respect to the aircraft, which is your true airspeed, which is the UA term. And then the horizontal winds are a function of heading and side slip angle, and the vertical winds pitch and angle of attack. So if you've been around for some of the multiple calibration flights we did, we were trying to get corrections for heading and pressure and everything so we can get all the little corrections out of the full equations here. So this is not the Falcon, this is the P3, but since I do it on that as well and I already had this slide, I just went with it. Basically what we have is that on the nose of the airplane, we have 5-hole port that gives you your impact pressure, and then the ones in the vertical will give you an angle of attack calculation, differential pressure, and the ones horizontal will give you your side slip angles. We also have on the Falcon, we have a non-de-iced total air temperature sensor, which is the fastest response temperature sensor you can get. But then you do get issues with icing, as we had several times, but it's a balancing act you have to learn to live with. And then we have pressure transducers to get the static and impact pressures off the one of the pressure ports from the aircraft. Internally, we have, or at least for the last 2 years, we had a new real-time data system that I'll talk about a little bit. We had an Planix that we used to get all the inertial data, where your aircraft is, pitch, roll, heading. For the last year, we had a piggy bank of many Planix that RSD was using to test out how well that works. So we had 2 Planix measurements. They actually worked very well together. We realized that we didn't have insert much support as part of the initial idea. So I actually became a mini insert and did the IWG1 data and broadcast it to the aircraft, and then we downlinked it through insert to the ground. We provided a time server from RSD that was used on most everybody's instruments to get a common network time protocol. And like I say, the data was downlinked. Eddie and Ewan did 99.9% of the flights. I did not ever fly on there because I barely fit to work on it, so I didn't get in there and fly. And the picture down here on the lower right, that is the radome of the Falcon after many penetrations in and out of clouds, and the water is beating the heck out of it. But the measurement still worked. Just for reference, the first year we used an old PC-based system that was also used on names and oracles. It works fine. It measured data up to about, I think I was doing 60 hertz during the first year, and then averaging it down for the archives to 1 hertz and 20 hertz. But we went to a more rugged real-time system for the last 2 deployments, and it's made by UEI DAC up in New England. It's really great. It's Linux-based. I had to learn Linux. That was a lot of fun. It's shock and vibration proof. It has individual timers for all of the A-rank channels and the analog channels. And the weirdest thing with this was I ran this at about 200 hertz, and the system likes to be run faster than that. So we actually had to work with them on learning how to slow things down. I can't imagine needing more data than that. And so we got all the A-rank data from my stuff, along with halfway through the second year of the deployment, we started reading in the A-rank from the aircraft because of icing issues with the total air temperature sensor, which was that one flight that Josh said that he didn't have data for. Basically, the total air temperature turned into a snow cone for the entire flight. And so we got backup data from the aircraft. We also had the analog signals, the Aplanics, and then an UPS for, making sure power is okay. And we broadcast it over the Ethernet and then downlinked it so I could watch it on the ground to make sure everything was okay. If you're really bored and want to know, this is what the full equation for the vertical winds looks like abbreviated. You have the vertical platform velocity, the true air speed, a term that involves the angle of attack and the side slip angle. These T1, T1C, T2, T3, T4 are transformations to get from the aircraft reference system to normal Cartesian coordinates, involve the pitch and the roll. And then you have your side slip angle and your angle of attack. In normal straight and level flight, a lot of this can cancel it out, so it approximates it. But so you can see all the terms that go into just getting, for all intents and purposes, a measurement that's almost zero. And if you average it over a few seconds, it's pretty much near zero. So you have a lot of issues with time lags, corrections, and trying to get everything lined up, but there's a whole lot of stuff that goes into getting a very, very small number. Current measurements and stuff like that. Like say, we switched data systems halfway through. We also recorded the IR temperature that was on the Falcon, the KT-19. That's in the archive data. We didn't lose data very much due to any type of acquisition issues. When we switched over to the real-time system, I lost data on part of a flight because I didn't realize that the hard drive was so small and it literally ran out of space during one of the flight because I collected so much data. But we got that resolved with an external hard drive. We'd lose data for icing issues. If we ran into some icing conditions, we'd lose stuff. We lost at least one or two pressure transducers during the missions, during all the flights, due to one of the lines with it's difference of pressure. It's a very small number. And if one of the holes ices over and the other one doesn't, it creates a bad, outside the range of the transducer, and it will kill the transducer. So we went through some of those. What I ended up doing is, after I started getting the data, and I think Ryan will follow up on this a little bit with the Hyatt flyer, we used the data from the aircraft, and what I would do is I would tie it to our data. We had calibrated our total air temperature to get the static temperature. We calibrated that, and so I tied the good data from the aircraft to that. So when we had issues with anything, we had a baseline for what the temperature should be. The data for the campaigns, all three of them are in. All three campaigns are in. Well, 6 deployments, 3 years. The data is all in the archive final. I did go back. I changed my mind each year for what I wanted to be put in the data set. So I went back afterwards and put them all to the exact same thing, as to not bug Michael too much or have Michael bug me, depending on how you look at it. There's two types of files in our archive. There's summary files. There's 1 hertz, which approximates a lot of what would come down in the IWG1 data, but it's actually been corrected and looked at. It's where the aircraft altitude, lat long, pressure, temperature, horizontal winds. There's no vertical winds in the 1 second data, because that number would be pretty much zero. There's also 20 hertz wind data, so you get the faster response. Pressure, temperature, winds, everything's in there. Surface temperature. I can produce data at higher rates if you want it. Just ask. The data is pretty much flagged for most non-straight and level flights, especially spirals and anything with large rolls. That data's been taken out because it just overwhelms that full equation, and we have issues. If you have areas you want to see with that data set, let me know. We can look into it. But I'd really caution you to use primarily straight and level data, please. There's no dew point data in there, because you should be using the DLH data for that. It's much better. It's text format iCart. I think they're trying to turn it into NetCDF. I don't know how to do that or read it, so talk to Michael. Like say, if there's icing issues, the data's been flagged out. We did several calibration flights since we'd not done winds on this system before, on this aircraft before. We did several dedicated calibration flights, so we got really good idea of what the, if we were to go back a little bit, let's see if I can just do this real quick, because I'm about out of slides. So for the horizontal winds, when you're flying along the wind, there's a pressure correction that's due to the fact that the compressibility of the air, of the wind around the aircraft, you're not getting a true ambient pressure signal. So if you were to go out along the wind and come back, your wind speed and direction differs without this correction. So we did enough reverse heading so we were able to get a really good idea of what that pressure correction was as a factor of airspeed. So we got that corrected out. The heading errors, when you put the Planix in or whatever inertial navigation system you're using, a change in your heading offset of like a degree will give you up to a couple meters per second difference in your wind speed. So every time that was taken out or put back in, we had to do more crosswind reverse settings to take care of that. We did a whole bunch of calibrations for the vertical winds and did speed maneuvers to get the angle of attack, offset, and slope. You know, we're like I said, we got to remember these are really big numbers coming out to become a really small number. So the calibration flights were were invaluable for getting those terms, and we actually did them very well. And it's kind of nice because I've done this more on the P3 than I've done on these planes, but now I'm having dedicated flights on the P3 to do the exact same type of stuff. And this, just for example, this is kind of what I look at on my, if you use Igor, this looks familiar, the type of plots I make. You can see the platform velocity and the resulting other term. They track each other very well. You see how it changes as the aircraft moves around. And you take the difference in these two numbers, and then you get the vertical winds with some of the areas, in this case, with big rolls taken out. And if you do you do a histogram of this, you should get a value that's right near zero for the entire flight. And all the flights pretty much look like this. The process study flights are a lot messier because that was a lot more in and out of clouds and different things. But the normal statistical survey flights look very, very good. And if we noticed issues like there was a couple of flights, January 11th and 12th, if I remember correctly, that we had some questions. There was icing on that flight, so I fooled myself and I used the aircraft temperature. So if you looked at the delta temperature, there was some issues with that because that's a slow response. That's like a 1 second response as opposed to a 20 hertz response, or actually a 10 hertz response on the total air temperature. So we had to go back in. If you notice, there's a couple of flights that were just recently updated. I was to go back. I went back and corrected the total air temperature, the fast response one, the best I could to get a better estimate for DLH and also for us for the vertical wind, so it looks much better. Same thing for the horizontal. Like I say, you can estimate the horizontal winds to first order using the heading, the ground track, the ground speed, and the true air speed. Sounds right. And so you can estimate what the horizontal wind speed and wind direction is. And if you compare that, that's the red line here. The blue is the full giant equations for them with everything. And you see with all the corrections in, they match up extremely well. Without the corrections in it, they would not line up nearly as well. To first order, for pilots don't care whether the wind speed is 3.2 meters per second or 3.6. They don't care. It's about 3. The wind direction can be off by 5 degrees. They also don't care. But for what we're doing, we need to get those corrections in and out, lined up, and you can even see it in the U and V components, east, west, north, south. We line up very well, depending, regardless of which of the two methods you use now to compute the wind speed and wind direction. I haven't actually gotten a lot of chance to go in and mess with the data. I've been too busy doing it and getting it in the archive, but Mike Brunke has a paper that he's used it for some of the stuff. Sonia has a poster in the back, and hopefully as the time goes by, I'll have more time to interact with her on this. I've been kind of busy doing other things. So, but there's been the data uses, and hopefully this year after Impacts ends, I will have more time to actually sit down and play with data. So that's all I have. If anybody has any questions. They're asleep.